Hi, I'm Tristan, and welcome to the CEA Structural Materials video. The total runtime for this video is about 12 minutes. We begin by defining exactly which part of the structure we are considering materials for, namely the outer layer. The part of the greenhouse that would be made of glass in a traditional design, the outer layer constitutes almost all of the greenhouse's exterior surface area, separating the inside from the exterior environmental conditions. We will not discuss the framework that supports this exterior layer. Although it is an important component, its thermal influence on the greenhouse is minimal, and its design is purely a matter of mechanical engineering. As a result, we consider its design outside the scope of this video, instead focusing on thermal issues pertinent to the structure. So now that we've defined exactly what we're looking at, how do we analyze it? Well, engineering materials selection works pretty much the same way regardless of what field you're performing it in. You define what material properties are relevant to the problem, come up with some manner of metric in order to sort them, and then select whichever material best fulfills that metric. So, what material properties are relevant to the construction of a greenhouse's outer layer? Well, let's go down the list. We start by breaking all of the substance's material properties into 4 categories: mechanical, thermal, radiative, and other. This helps us look at them individually and breaks the problem down into more manageable units. Now, some viewers may be noting that you can't actually separate material properties in this way. For instance, the mechanical properties of a substance will often change in response to changes in temperature. This is true. However, it would be unnecessarily complicated to model all of the material properties of a substance under every possible set of environmental conditions it would be exposed to. Rather, depending on how exactly a given material property changes, we either take its median value or its worst value. For instance, when looking at insulative properties, we would take the median value since we are concerned with overall heat loss, while when looking at strength and ability to resist fatigue, we look at worst value since the greenhouse either collapses or it doesn't. This allows us to assemble a list of material properties from which we can begin to exclude irrelevant terms. We start by looking at the mechanical properties. Most of the mechanical properties we can dismiss out of hand as irrelevant because we're not looking at the support structure. As long as the material we use has a very basic level of strength, enough to support its own weight, its exact strength is irrelevant since we're not going to be using it as a load-bearing substance. The 2 material properties we do care about then are resistance to fatigue and density. The reason we care about these 2 is because resistance to fatigue is one of the contributing factors to the material's lifetime, which we will discuss later. Density, on the other hand, is important because of the supporting frame. A denser material requires a stronger support frame, which increases cost, allowing us to represent density as an adder to the material's cost rather than as an independent term. This eliminates the last of the mechanical properties, allowing us to move on to thermal properties. As with the mechanical properties, we can eliminate most of the thermal properties right off the bat as being irrelevant. We won't be heating the material to the point that it melts or bursts into flames, and its coefficient of thermal expansion is only relevant if it causes problems with the frames the material is mounted in. Specific heat could be relevant in that it takes heat from the greenhouse, but unless the specific heat is so high the building begins to act as a heat sink, we can dismiss it as irrelevant, as the greenhouse material will come to the surrounding environmental temperature. This leaves us with the 2 thermal material properties we do care about: the R value, or resistance to conductive heat transfer, which we will use at almost every step of our greenhouse structural analysis, and its resistance to convective heat transfer, a more specific value we will only use in a few very detailed analyses. Nonetheless, it is relevant to greenhouse structural design. Continued in Part 2.